Hi guys, in today's video I'm going to show you on how we're going to write Verilog code, okay, for one big module consists of several small module. Okay, how we going to achieve this? Okay, how we going to write one big module, or how we going to call the small module inside the big module? Okay, we're going to do that by using instantaneous. Okay, as I mentioned in the class, there are two types of instantaneous: instantaneous by order, another one instantaneous by name. Okay, by using two different methods, we can achieve, or we can write a big module consists of several small module. Okay, why we have to do like this? Why we have to call several small module? Because it's going to make our life easier. Let's say in one big design here, okay, you have a several let's say adder, several adder. You don't have to write, okay, the adder here several times. You only have to write one time. Then after that, you can give a special name, a unique name, and call them back. Let's say this one half adder 1, half adder 2, let's say half adder 3. So you can call each one of them as many times as you want inside this one big module here. Okay, that's the idea why we have to use instantaneous to create one big module, to save your time, to make your life easier. If you see in like C programming, it's more like when you want to call a function. Whenever you have a function, you can call the function as many times as you want. Okay, it is not like every time at that particular problem you have to create that particular code. No need. Okay, you just have to call back the function that you have written before, okay, to achieve that particular task. Okay, the same thing here. Now we want to write one big module here, okay, where it's going to consist of several small modules. Okay, how are we going to do that? As I mentioned, we're going to use the instantaneous technique. Okay, there are two different type of instantaneous: instantaneous by name, instantaneous by order, and instantaneous by name. Okay, let's say in this particular example here, I'm going to show you how we're going to create a 5 bits, okay, plus 5 bits, okay, full adder, okay, consists of, this is the big module that we want to achieve. Okay, big module, the main module. Okay, let me give you just a general name. It's a big module, or it can be a main module. Okay, big module. Okay, inside this 5 bits plus 5 bit, you're going to have a full adder. Okay, full adder. This one going to be the small module. Okay, then inside this full adder, you're going to have a half adder. Okay, small module. Okay, so whenever you want to call, let's say 5 bits plus 5 bits, okay, going to have several full adder, right? So you can call as many times as you want. Like say 5 times, you can call full adder 1, full adder 2, and so on. Okay, same thing here. Let's say in half full adder, it's going to consist of several half adder. Okay, you can call that particular half adder module several times as well. Okay, now we're going to look in detail how we're going to achieve this particular example here. Okay, for that, let me try to have a look first. Okay, the truth table for the half adder. Let's say this is the half adder. Okay, how the truth table going to look like? We have two input, right? A and B. Then, as you know, we're going to have two output as well. C out, okay, and also carry out, and also sum. Let's say we have 0, 0, 0, 1, 1, 0, 1, 1. Okay, 0 plus 0, 0, 0. Then 0 plus 1, 0, 1. 1 plus 0, same 0, 1. 1 plus 1, 1, 0. It's simple adder. Okay, if you plus 1 bit plus 1 bit, you're going to get, okay, 2. Okay, now our task is we already have written the truth table. Okay, now we can represent this truth table in the form of logic gates. If you can see clearly, this C out, okay, can be represented by AND gate. Okay, this sum here can be represented by XOR. Okay, you can see from the output pattern itself. Okay, now our task is to, okay, let me draw first the gate. Okay, we have a XOR gate for the sum, where it consists of two input A and B. Then okay, this is for the sum. Then we have okay, the same input going to flow to the AND gate. Okay, this one going to be C out. Okay, so this is the block. Let's say we want to write in the form of block. Okay, this is the block for the half adder. So now we're going to write a Verilog code, okay, for the half adder, where it consists of input of A and B and output of sum and C out. Okay, as I mentioned to you in the class, there are three different ways for you to write the Verilog code for the half adder. You can write in the form of gate level. Okay, you can write in the form of data flow, and you can write in the form of behavioral. Okay, either one. Okay, you can choose on your own. Let's say now we create. Okay, I'm going to show you simultaneously the Verilog code as well. Now let's say I want to create a half adder. Okay, project. You can give any other meaningful name if you want. If you don't like a half adder, because I'm creating the first half adder, right? You can give like a complete adder. Let's say complete adder. Let's make it C and A capital. Complete adder. All right. Next. Okay, this is the specification for the Spartan 3E board that we have. Okay, make sure all the family, device and package correct. Then go to next. Then you're going to have the summary for the project. Click finish. Okay, now we're going to add a new Verilog file. Right click and go to new source. Okay, choose Verilog module. I want to create my half adder first. Okay, go to next. Okay, next, finish. Okay, now as I mentioned, you can write your coding in any method that you like. It's up to you. All right, now I'm going to declare the directivity input for the A and B, then the output for the sum C out. Okay, now let's say I want to write in the form of the gate level. So what I can do, I can call XOR first, okay, the gate, then give a special name XOR1. Okay, what is the output? Sum. What is the input? A and B. Then I have what? I have AND gate, then give a special name for the AND gate, and 1. Then what is the output? C out. Okay, what is the input? A and B. Okay, that's all. We have successfully created half adder. Go to save it. Okay, go to simulation, click on it on the Verilog file, check the syntax whether there are any error or not. Okay, syntax has been completed. Okay, no error. All right. Okay, now the next step that you can do, if you want to do, you can create a test bench file and create and see whether you are getting the expected output or not. Okay, you can do that. All right. Okay, or else I want to continue this because I already know, because these are only 2 lines of coding. Okay, it is not that hard for you to see the output. Okay, now I want to continue to write the coding. Now I want to use this half adder that I have created. See this half adder that I have created to create a full adder. Okay, now my task is to create a full adder by calling that a small adder. How I'm going to do that? Okay, now I already have one half adder. Okay, half adder 1. I have input A and B. Then I have the output. Okay, I have sum and C out. Then I need another half adder here. Okay, half adder 2. The input now, okay, let's say now the input to this particular half adder, okay, going to come from where? Okay, it's going to come from the first sum. The sum going to be the input for this particular number 1. then the C out, okay, the C out, okay, going to flow here, okay, it's going to be or by another C or by another C out from the half adder 2, okay, or okay, this one's supposed to be C out, okay, this one's supposed to be sound. And what is the another input for this particular half adder? Okay, it's supposed to be C in, because in full adder we're going to have 3 input, A, B and C in. Okay, you can have a look in detail by writing the truth table for the full adder. Okay, if you write the truth table, okay, for the full adder, you can get the idea how we achieve this particular 2 half adder here. Okay, it's quite simple and straightforward, easily. Okay, easily you can do that without any problem. All right, now I want to show you how we're going to achieve this particular full adder. Now we have for the full adder block, okay, A, B and C in, A, B and C in. Okay, the output I have sum and C out. Okay, now we're going to create, let's say this is the block here, this is the block. Okay, this is the block here represented here. Okay, inside this full adder we can see you have 2 different half adder. How you going to call, okay, these 2 different half adder inside this full adder? So now we're going to use the help of the instantaneous technique. Okay, let's say, okay, now let me proceed here. Now let me proceed here. Okay, now you want to write another model, right? Another model for the full adder. Full adder consists of what? You can see here the input A, B and C in, right? A, B and C in. Then we have what? Sum and also C out. Okay, this is the input output port for the full adder. You can see here, this is the full adder that you want to write the Verilog code. Okay, it consists of 2 different half adder. How are you going to connect them? Okay, now, okay, the same thing. Now you're going to define the input, okay, A, B, C in. Then you're going to define the output, okay, sum and also C out. Okay, how are you going to call the half adder? So what you're going to do, you come here, copy this line, copy this particular line here, copy, Control C, come here, Control V. Okay, now what you're going to do, give a special name, half adder 1. Okay, you're going to call the full, okay, this is the module name. Okay, then you're going to assign a unique name to this module, because you have 2 different module, right? You have half adder 1 and half adder 2. Okay, your task is to connect the, okay, half adder 1 to the half adder 2. Okay, now let me see here, we have supposed to have, okay, one complete line there. All right, now, okay, I'm going to write, okay, 1 half adder. Okay, now we can see, right, the output of the sum from the half adder 1, okay, going to be connected to the input half adder 2. So this one going to be a wire. Okay, you can declare as a wire, let's say W1. Okay, this one going to be a W1. Then also we can see here we can have another output from the half adder 1 connected as the input to this particular OR gate. This one going to be your wire 2. And also we can see here this output also connected as an input here, going to be W3. You can have 3 wire there. Okay, come back here, declare W1, W2 and W3. Okay, now what we have here, you can have, okay, the output here, okay, supposed to be what? The sum now represented by the W1. So remove the sum and put W1. Now the C out represented by the wire W2. Okay, right, W2 there, W2. Okay, now call the half adder 2. Okay, copy back this one, copy the initial one, easier for you. Copy, Control C, come back here, enter, Control V. as I mentioned, give a unique name, half adder 2. Okay, now what is the input? What is the input here? Input, for the input, the first input here going to be W1. Replace the A with the W1. Okay, how about the input B? Going to be now C in. Okay, B replaced with C in. Okay, how about the output here? Sum. Okay, sum, just leave it, no problem. Then where the output, another output C out, going to be connected to the OR gate. So replace the C out with the W3. All right, that's all. Now, is it complete yet? No, we only have defined two half adder but haven't defined yet the OR gate. Okay, what are you going to do now? You're going to call the OR gate, or give a special name, O1. Okay, what is the output of the OR gate? C out. C out. What is the input? We have W2 and W3. So we have W2 and W3. Okay, that's all. And module. Every time you start with the module, you're going to end module. Okay, now you can create a command there so that it'll be easier for you. Let's say okay, this one initially what? Half adder. Okay, easy for you later if you want to recall back. Whenever you cannot find anything, then you can come back. It'll be easier for you. Okay, okay, to if you properly define anything, it'll be later easy for you to find where you write the coding for the half adder, where you write the coding for the full adder. You can come back and refer back. Okay. All right, now you have completed the coding for the full adder. Okay, now try to save this file. Have a look here. Have a look here carefully. Once I press the save button here, or the save icon here, you can automatically see the full adder will become the main module. Okay, as a sub module, you can see the half adder. Save. There you go. Inside this particular full adder here, we have two half adder, as I mentioned before. Okay, now this is what we call that. Okay, instantaneous by order. Okay, because we exactly follow the same order here. Okay, so that's why we call that instantaneous by order. All right, so now, okay, now you can write a test bench file for the full adder and test. Should be no problem. You can add as many as test bench file that you want, no problem with that. But now, if you want to create the test bench file, okay, you're going to give a 3 different input, then you're going to observe the output, what is going to happen there. Okay, this is a simple full adder. If you give a 1 1 1, okay, you're going to expect the output 1 1. Okay, if you give a 0 0 1, you're going to expect, see, 0 1. Or if you give a 0 0 0, the output going to be 0 0, because this is adder, right? Adder, as simple as that. Adder, it's like a calculator. Okay, now I'm going to continue because my main idea, my main intention or main objective, I want to show you on how we're going to call the small module inside this big module. Okay, now as I mentioned before, okay, now we want to create a 5 bits plus 5 bit adder. Let's say 5 bits, okay, plus 5 bits full adder. How are you going to do that? Okay, initially you have created a full adder, right? Okay, full adder. You have a okay, one complete full adder, right? Okay, this particular complete full adder. Okay, full adder. What do you have? You have A, you have a B, you have C in, then you have what? C out, and you have sum, right? Now for the 5 bits, okay, this one, as you can see previously, this one 1 bit plus 1 bit. Okay, we have A 1 bit and B A 1 bit and B also 1 bit. 1 bit plus 1 bit. If you want to create, okay, for the 5 bits plus 5 bit, you must call back the full adder 5 times. So let's say this is a number 5. Okay, then I'm going to create another module here. Okay, we're going to connect the C out to the C in. This one going to be A5, B5. So this one's supposed to be C5. Okay, now you have A, B, A4, B4. Okay, now you're going to continue to do the same thing. Okay, 3, 4, 5. Okay, you're going to connect the output. Okay, I'm going to write this first. Okay, going to be here. Some 1, some 2, some 3, some 4, some 5, some going to be C out. So you can see the C out from one output connected to the next input. Okay, C out will be the C in for the next full adder. Okay, this is the full adder for 5 bits plus 5 bit. Okay, if you write in the one big module, it's going to look like this, something like this. 1, 2, 3, 4, 5. Let's say A5, A4, A3, A2, A1. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. Let's say B5, B4, B3, B2, B1. Then we have what? C1, C in, C in. Then we have 1, 2, 3, 4, 5. 1 C out. Then we have some 1, some 2, some 3, some 4. Let's see out. So this is the 5 bits plus 5 bits full adder. Okay, now our task is to write this particular, okay, the Verilog code for this particular 5 bits plus 5 bits. How are we going to do that? Since we know that we're going to call the full adder, all right, continue here, the coding here. Let me continue to write. We can see instantaneously what's going on. All right, so now as I mentioned before, 5, this is the command, 5 bits full adder. Okay, now I'm going to what? I'm going to create the input here, the module for the 5 bits. 5 bits adder, module 5 bits, okay, full adder. Okay, what is the input? As you can see here, we already write the, okay, we already write the input and output, right? Okay, the input supposed to be A, B, C in. What is the output? Sum, C out. Okay, now you're going to define the directivity. Input supposed to be how many bits for the A you have? Okay, 5 bits. So 4 to 0. 4 to 0 for the A. Same goes to the B as well. Okay, then we have input. Okay, only 1 bit for the C in. Then we have what? We have the output. Okay, for the sum. Same also we have 5 bits. Okay, 4 to 0. All right. Okay, sum. Then we have output. Okay, C out. Okay, you can write the end module first. All right. Okay, now you're going to call the full adder, right? Because here we have 5 different full adder inside this one big 5 bits adder, right? So as I mentioned before, copy this particular line here. Control C, bring it here. Okay, give a unique name. Let's say we want to start from here. Full adder 1. Okay, what is the input for the full adder 1? A1, B1, C1. So give a, let's say A0, because you can start here from 0, 0, 1, 2, 3, 4. Okay, we have 5 bits, right? Same. It's the same as long you can understand what you're writing here. A0. Then we have what? B0. Okay, then we have what? C in. Okay, correct. C in. Then we have what? Sum 0, because here we declare start from 0, right? Okay, then we have what? The C out. The C out here going to be what? Okay, the output from this full adder is connected to the next full adder, right? So it's going to be wire. So we need to declare the wire. Come back here, declare wire. Wire W1, W2, W3, W4. Okay, if not enough, we can add, no problem. See, this is how you write the coding. It is not like you're going to know everything initially. No, first draw the block diagram. If you can see something is missing, then you can come back and proceed back. So here is supposed to be what? W1, W2, W3, W4. 4 different wires. Alright? Okay, come back here. So instead of writing C out, here you can see W1, right? Connecting to the input there. So it's going to be W1. I'm writing each one of them individually. Or you can write in the form of a vector. You can write in the form of like this. We have 1 4 different, right? Because 3 to 0 W like this as well, no problem. Okay, now I put here as a comment. It's not going to affect the command there. Okay, this is just a comment for your own reference. Okay, it's not going to affect our coding overall. So now I already I already here written for the coding for the full adder 1. Now I'm going to repeat the same process to the following full adder. So the simplest way, just copy this line. Okay, just copy and paste. How many times? 5 times. 2, 3, 4, 5. Now your task is to change the name properly. Now you have to give a unique name for each one of the adder. Number 2, number 3, number 4, and number 5. Here we have A0, A1, B1, A2, B2. They have A3, B3. They have A4, B4. Then we have what? C in now going to be replaced by the wire, the following wire. W1 going to be here, okay, connected here as well, W1. Then, okay, the sum 1, okay, sum 1, sum 2, sum 3, sum 4. Then here we're going to replace with W2. Here, see, the wire is supposed to be W2, right? Okay, W2, the wire, the same wire going to be for the next full adder. So, W2. Here going to replace with W3. Here also going to be the same W3 wire. Okay, one wire output going to be the input for the another one. Okay, W4. Here also going to be the W4. The finally, what is that here? You can see the sum C out. C out. That's all. Finish. It's quite easy, right? Okay, now try to see here the 5 bits full adder haven't appeared yet. Once I click save icon here, you can see here what's going to happen. Now have a look. There you go. So inside this 5 bits full adder, we have 5 full adder. Inside of each one of the full adder, we have 2 half adder. See? This is what we call by instantaneous. We have successfully created one big module here. Okay, consists of several small module. Okay, this is like a Russian doll. Inside one doll, we can have another doll. Inside one doll, we can have another doll. Something like that. Now we can write a full test bench file to test our 5 bits full adder. Okay, come back here. First of all, you can check whether the syntax is correct. Okay, click this full adder file. Okay, everything is correct or not. Check first. Okay, perfect. Behavioral check syntax completed successfully. Okay, come back here, right click, add a new source. Going to be Verilog test features. Okay, going to be test bench file. Next, next, finish. Okay, now come back here. You're going to give an integer, right? I want to create 3 different integer. 3 different integer for A, B, and C in, because we have 3 input, right? So integer I, J, K. Okay, now come back here. I can add the stimulus here. Okay, I'm going to create 3 different for loop for I equal to 0, I less than 2. Now I'm going to repeat. I'm going to assign I to the C in. Okay, so C in going to be either 0 or 1. Okay, I equal to I plus 1. Okay, then begin. Okay, I'm going to assign C in equal to I. Okay, then I'm going to give a delay 2 nanosecond. Okay, now I don't want to close the loop, but I'm going to assign now the input for the A. So I just copy this line. It'll be easier for me. Control C. I come back here. Control V. Okay, make it properly. Okay, now I'm going to replace the variable I with the j. Okay, now j going to be how many bits? A going to be 5 bits, right? 2 to power of 5 going to be 32. Okay, replace everything with j. So C in now going to be a equal to j. So a going to take the value from 0 until 31. Okay, same thing here. I'm going to copy this line. Now I'm going to paste back here because this is a nested loop, right? You can see inside one loop we have another loop. So now I'm going to give an input for the b. I'm going to be k, same. B also we have 5 bits, right? 2 to the power of 5, 32. Here also we have k. I'm sorry. Control Z, k. Now B, okay, we will take all the value from the k. Now I'm going to close the loop, begin, and close this loop, and close this loop, and that's all. Try to save and check any syntax error. Okay, Bismillah. Okay, stimulate behavior model. Double click. See what's happened there. All right, we're going to have a look. Okay, now what we can do, change this all binary into decimal. Okay, unsigned decimal. Okay, now we're going to have a look in detail. Okay, let me try to zoom. You can see what happened here. Okay, you can place any cursor to any of the timing diagram. You can see. Okay, let me try to. Okay, now try to have a look here what happened. Okay, here we can see 13 plus 4, 17. So 13 plus 4 equal to 17. Okay, now let me see when we have a different C in as the output here. Okay, get to complete that, you can run and let the simulation complete. Okay, you can see from here. I can see. All right, you can see from there. 14 plus 30 plus 1 is supposed to be 45. So we can group together sum and C out. Okay, make it one group. Okay, create new virtual bus. Okay, change the virtual bus to the unsigned decimal. Okay, now you can see. Okay, now the C out is the most significant bit, right? Okay, then only sum. So now you can see 45 as our output. Okay, let me try it another one. See this one. We have 31 plus 12, 43, 43 plus 1, 44. So we can see our result, okay, according to the Verilog code that we have created. 10 plus 17, 27 plus 1, 28. All right. Okay, hope you enjoy this video and you can understand more about the instantaneous module to create one big module. All right. Thanks, guys.